In this video, we're going to cover section 3.3 in the linear differential equations class, and that is complex roots of the characteristic equation. So I'd like to point out that the homework for this section will be 5 through 15, so make sure you look at that and do that. All right, now to get started with this section, we are going to do, we're going to say that here that a reminder from section 3.1 that we noted, in there we noted that the solution to the homogeneous second order linear differential equation, and that homogeneous equation is ay double prime plus by prime plus cy is equal to 0. The solutions to that had the form y equal e to the rt, where r is a root to the characteristic equation ar squared plus br plus c is equal to 0. Well, furthermore, if the roots of this differential equation are real and different, we can call them r1 and r2, then y equal to c1e to the r1t plus c2e to the r2t was the general solution. So that's going to happen here as well if the roots to the characteristic equation are complex. So let's look at what happens there, right? So if the roots are complex, then the corresponding expressions for y are y1 is equal to e raised to the lambda plus I mu times t, and y2 is equal to e raised to the lambda minus I mu all times t. Right, and notice here, right, if r is, the root is a complex value, lambda plus I mu, then the other root is its complex conjugate, lambda minus I mu. So those would be the two r values here, and we just replaced r with those complex values, and we get e to the, again, lambda plus I mu t as our first solution, and then the complex conjugate in for the second solution. I would like to point out here for those complex values, of course, lambda and mu are real numbers. So don't get that confused with previous sections where we used mu as our function for an integrating factor. That is a real number here. Our solutions are here. But the problem is, how do we deal with that? How do we deal with e raised to a complex value? To deal with that, we actually use Euler's formula. I'm not going to derive that here. It's in the book if you'd like to look at it. But that formula is e to the it equal to cosine of t plus I sine of t. Or more generally, e to the I mu t is equal to cosine of mu t plus I sine of mu t. So e raised to the lambda plus I mu t is e to the lambda t plus cosine of mu t plus I e to the lambda t times sine of mu t. And that's what we're going to use here in a bit, but we'll see how to use that in our first example, and only example actually. Before we do our example though, I want to look at a theorem. And this theorem is actually in section 3.2, but we didn't cover it in that section because really it kind of fits more in this section 3.3. This is really when we're going to use it, so I waited to mention it until now. Consider the second order linear differential equation L of y equal to y double prime plus p of t y prime plus q of t y equal to 0, where p and q are continuous real-valued functions. If y is equal to ut plus ivt is a complex-valued solution of this differential equation, then its real part u and its imaginary part v are also solutions of this equation. So again, what does that tell us here? Right, if we have a solution, then its real part and its imaginary part, each of those are solutions. And that's going to end up being how we find our fundamental set of solutions. But again, we will see that in this example. I've already written out the example, so we're just going to kind of go through this now. So example 1, and again, this is the only example we're going to go through in this section, is Let 16y double prime minus 8y prime plus 144y equals 0. That's our differential equation, our homogeneous second order linear differential equation. And we have these initial values. Y of 0 is -2 and y prime of 0 is 1. We want to solve this initial value problem. How do we do that? Well, we first write out the characteristic equation. 16r squared minus 8r plus 145 is 0. And then we solve that. And we want to use our quadratic formula. Working out our quadratic formula, we get 1/4 plus or minus 3i is the two complex roots to this equation. So we have those. And you can pause the video if you'd like to verify and go through this calculation. But this is the end result. So we go ahead and plug that in. We get e raised to the 1/4 plus 3it, we're just looking at one of our solutions here, is equal to e raised to the 1/4 t times cosine of 3t plus I e to the 1/4 t sine of 3t. And this came from that very last formula we wrote on the first page when we were talking about Euler's formula. So you can go back in the video and verify that or check that. Okay. So what do we get? Well, this gives us two solutions, right? So via this theorem above, the real valued part is a solution. So y1 equal to e raised to the 1/4 t cosine of 3t is a solution. And the imaginary part is a solution. So y2 equal to e to the 1/4 t sine of 3t is also a solution. All right, so then the question is this really a fundamental set of solutions? Well, to check that, we need to calculate the Wronskian. So what is the Wronskian? Reminder that is y1, y2, y prime 1, and y prime 2 here. Again, y1 was e to the 1/4 t cosine of 3t, y2 was e to the 1/4 t sine of 3t. We're going to calculate this determinant, and y prime of 1 is written here. Just to make sure that y'all can read that, it's e to the 1/4 t times -3 sine of 3t plus cosine of 3t times 1/4 e to the 1/4 t. Right? We do product rule. We do the product rule again here for the second one, for y2 prime. And that is e to the 1/4 t times 3 cosine of 3t plus sine of 3t times 1/4 e to the 1/4 t. We calculate that determinant. That is written out here. That gets a bit lengthy, but I suggest that you can go ahead and calculate that on your own as well, but it's written out here. We calculate that determinant. It reduces all the way down to 3 times e to the 1/2 t. And as a reminder, since that is not 0, what that means, if the Wronskian is not 0, that tells us that y1 and y2, again, y1 and y2 are these two functions. y1 is here, y2 is here. Those two functions form a fundamental set of solutions. What does that mean? That means the general solution is C1 times the first solution plus C2 times the other solution. So again, our general solution is y of t equal to C1 e to the t over 4 times cosine of 3t plus C2 e to the t over 4 times sine of 3t. Well, we're not quite done because, again, we want to solve the initial value problem. So we have the general solution here. We plug in our first initial value, and that is y of 0 is equal to -2. That gives us -2 equal to C1 times 1 plus C2 times 0. So -2 is C1. Furthermore, then, we continue along, and we want to plug in y prime of 0 is equal to 1 in, and to find C2, so help us find C2. Well, to do that, we need to first calculate y prime of t, which we do here, right? Our general solution was y of t, so we just calculate y prime, and we get c1 times e to the t over 4 times negative sine of 3t times 3 plus 1/4 e to the t over 4 cosine of 3t. And all of this is added to c2 times this, which is e to the t over 4 times cosine of 3t times 3, plus e to the t over 4 times 1/4 times sine of 3t. Again, just applying the product rule appropriately. Plug in 0 for t and 1 for the y value, and we get 1 is equal to 1/4 c1 plus 3 times c2. c1 is negative 2, so we plug that in and carry this calculation through, and we end up with c2 is equal to 1/2, which tells us our solution to that initial value problem is negative 2 e to the t over 4 cosine of 3t plus 1/2 e to the t over 4 times sine of 3t. And that's all I want to cover for this section. Make sure you do the homework. And of course, review this video and read through the section to get more examples. But that should set y'all up to be able to work through these sections. If you have any questions, please feel free to email me and I will get back to you as soon as possible.